Tonight, let your mind drift to the film Interstellar. Imagine the ship, Endurance, sleek and silent, slipping through the blackness between stars. It moves across a dark field that seems to have no end. The motion is calm, yet the sheer distance around it feels immeasurable. The craft glides between stars, as if the space between them is simply a quick, long road. It is a beautiful dream of easy travel across the cosmos. In reality, the first observations of deep space revealed a very different picture. When early astronomers pointed their instruments toward nearby stars, the signals showed almost no change. The stars did not drift across the sky in ways that matched our common sense. Year after year, their positions shifted only by tiny, tiny angles. These shifts were so slight a movement only visible after years of patient watching. This pattern was the same for every star they looked at. Even the closest stars behaved as though they were frozen behind an invisible wall of distance. Their faint movements suggested that the empty space separating them dwarfed the size of our entire solar system. The data offered a quiet clue. The emptiness between the stars was not a short gap. It was a fundamental feature of the cosmos itself. As more measurements were collected, the truth became clearer. The space between stars is not simply a longer version of the space between planets. It is a region defined by time. Even light, the fastest thing we know, needs years to cross the space between stars. The nearest star system, Alpha Centauri, is more than 4 light-years away. A familiar comparison helps us understand this scale. Commercial aircraft cross continents in hours. Spacecraft inside our solar system require many months or even years to reach distant planets. Yet, if one of those spacecraft continued toward Alpha Centauri at its current pace, the trip would extend beyond the length of all recorded human history. This is not a failure of our machines. It is simply the nature of the universe. The cinematic image of smooth travel between stars remains appealing, but the steady truth from astronomy shows a consistent reality. The universe places stars vast distances apart, forming empty regions that were shaped over billions of years. This incredible scale is the first and most enduring boundary for any attempt to move between the stars. The fastest spacecraft built by humans travel through the solar system at speeds that feel immense in everyday terms. New Horizons, one of the fastest probes ever launched, crossed the distance from Earth to the Moon in roughly 9 hours and continued outward at more than 14 kilometers per second. This performance far exceeds the capability of any aircraft and goes far beyond the speeds of ordinary human experience. However, once these speeds are compared with the scale of interstellar space, their limits become clear. The distance to Alpha Centauri, the nearest star system, exceeds 4 light-years. A light-year is the distance that light covers in 1 year, moving at nearly 300 million meters per second. When a probe like New Horizons moves at a tiny fraction of that speed, the travel time expands into tens of thousands of years. The structure of the solar system also illustrates this contrast. Planets orbit the Sun within a span of light travel time measured in hours and days. Spacecraft operate comfortably within this range. Beyond this region, the density of matter drops sharply, and the distance between objects increases dramatically. Observations over decades show that stars drift only slightly against the background of the sky, revealing the true, immense distances involved. Historical measurements reinforce these findings. Early parallax studies in the 19th century showed that even the closest stars shifted by tiny, almost imperceptible angles when Earth moved around the Sunday. These minimal motions indicated that the stars were far more distant than any planet. The results aligned with later radio and optical data collected in the 20th century, all confirming the same incredible scale. An everyday example helps clarify the scale. A person walking across a room covers a distance that light crosses in a literal flash. A commercial aircraft traveling between continents takes many hours, while light makes the same journey in a fraction of a second. When this comparison is extended to spaceflight, the situation becomes extreme. A spacecraft that seems fast within the solar system becomes all but motionless when measured against interstellar distances. The limitation does not arise from a technical flaw in propulsion systems. It reflects the fundamental size of the galaxy and the distribution of stars within it. The physics of motion means there is no practical way for current spacecraft to close such a gap within a human lifetime. The speeds required exceed what known materials and energy sources can safely provide, establishing a clear boundary for present-day interstellar travel. The speed of light sets the ultimate limit for how fast anything with mass can travel. Light moves at nearly 300 million meters per second, and nothing we know of can reach or cross that speed. The limit emerges not from an engineering problem, but from the fundamental structure of space and time itself. When an object accelerates, its kinetic energy increases. In everyday life, this relationship seems simple. A car needs more fuel to go faster, but the increase remains modest. But at much higher speeds, this relationship dramatically changes. As an object approaches the speed of light, the energy requirement grows exponentially. The amount of energy needed to gain even a little more speed approaches an infinite amount. This behavior was first proven in the early 20th century. Experiments showed that high-speed particles in accelerators required increasing amounts of energy for only tiny boosts in velocity. The data perfectly matched the predictions of relativity. The particles could move close to the speed of light, but could not reach it. This pattern has repeated for more than a century across every technology we have created. A comparison helps clarify the scale. A person running faster needs more food energy, but the required increase remains modest. For a spacecraft attempting even a small fraction of light speed, the energy cost becomes truly enormous. Even an incremental rise in velocity demands energy far beyond what chemical rockets or nuclear systems can safely supply. The challenge is not only generating the energy, but storing and managing it safely on the journey. The vastness of the galaxy adds another challenge to this problem. Stars and planets formed over long periods, and their motions follow orbital patterns shaped by gravity on a large scale. The distances between stellar systems reflect these ancient formation processes. Because the separation is so vast, a craft would need to sustain near light-speed travel for extended periods to cross even the nearest gap. The energy wall fundamentally prevents this from happening with any known method. All observations and theory point to the same unchanging conclusion. The speed of light acts as a structural boundary within the universe. No material object can cross it, and approaching it requires energy input that grows without limit. This boundary defines a primary physical obstacle to interstellar travel using conventional propulsion. Time is the first major barrier we face when travel extends beyond our solar system. The distances between stars are so immense that even very high speeds would produce travel times far beyond a human lifespan. The structure of time, in this context, is not a poetic idea, but a measurable constraint observed in astronomical data. Early star catalogs revealed that stellar positions changed only slightly over long intervals. These small movements, known as proper motion, show that stars move through the galaxy, but they do not significantly alter their apparent positions over short periods of time. If a nearby star seems almost fixed in place over decades, then any attempt to reach it must account for journeys that span many human generations. The solar system offers a familiar comparison. Signals from Earth reach the Moon in a little more than 1 second and reach Mars in several minutes. These small delays are noticeable even when communicating with our closest probes. When the scale shifts to the nearest stars, the delay grows into years. Light from Alpha Centauri requires more than 4 years to reach Earth, and a spacecraft traveling at a small fraction of light speed would require a period that stretches into tens of thousands of years. Our own biology reinforces this barrier. Human lifespans are fundamentally limited, and long exposure to low gravity, radiation, and isolation presents immense challenges. Experiments aboard space stations show that months in microgravity lead to muscle loss, bone density reduction, and changes in fluid distribution. Extending these conditions to the multi-decade spans required for star travel introduces risks for which we have no established solutions. Histories of exploration on Earth illustrate a similar pattern on a smaller scale. Long sea voyages consumed months and relied on large crews and supplies. Even then, survival depended on constant replenishment and navigational skill. Interstellar travel shifts this framework into a realm where resupply is impossible. A navigation must operate across time periods that far exceed human experience. Astronomical measurements, biological limits, and engineering constraints all tell the same story. Time imposes a structural limit that fundamentally shapes every attempt to imagine travel between stars. The duration required for the journey becomes an obstacle independent of propulsion and technology, forming one of the core, inescapable challenges of interstellar exploration. The nearest stars sit at distances that make our familiar measuring tools seem useless. Within the solar system, distances are often expressed in kilometers or in units based on the Earth-Sun separation. These measures remain practical when describing planetary orbits and spacecraft trajectories. Beyond this region, they begin to lose descriptive power. The Alpha Centauri system provides a clear example. It lies more than 4 light-years from Earth. 1 light-year is the distance light travels in a single year, moving at almost 300 million meters per second. When this distance is converted into kilometers, the result reaches a figure with 13 digits. The resulting number is so vast that it no longer connects easily to any sense of scale we use in daily life. Astronomers recognized this enormous gap early in the study of stellar positions. Early observations showed that even the closest stars shifted by only tiny angles when Earth moved along its orbit. The small size of these shifts indicated that the stars were far more distant than planets. As instruments improved, The data confirmed that such distances were typical across the local region of the Milky Way. The underlying structure of the galaxy explains this pattern. Stars often form within vast clouds of gas and dust. Over long periods, gravity gently pulls these stars along huge orbital paths around the galactic center. The result is a distribution in which stars are separated by several light years on average. This spacing serves as a kind of built-in scale, similar to the way buildings in a city occupy blocks rather than standing side by side. An everyday analogy helps frame this distance. A person can cross a room in a few steps. A city can be crossed in an hour by car. A continent requires many hours of flight. These layers of scale already feel different in the mind. Moving from planetary distances to interstellar distances adds another jump that exceeds this ladder. The space between stars is an empty expanse that stretches far beyond any journey we can take on Earth. Current spacecraft performance highlights the contrast. Even probes that have left the orbit of Neptune still remain deep within the Sun's sphere of influence. Their paths will eventually carry them into interstellar space. But their slow progress clearly illustrates how slowly, even fast, machines move when compared to the size of the galaxy. The nearest star continues to appear almost fixed in the sky because the separation is so large that human lifetimes are too short to register significant change. The feeling that a nearby star is as distant as a galaxy emerges from this combination of scale, history, and observation. The distances between stars are not simply long. They mark a structural layer of the universe that defines one more barrier for interstellar travel. Interstellar space is often described as an empty region, but measurements show that it contains a structured environment shaped by gas, dust, radiation, and magnetic fields. These components exist in extremely low densities compared to the familiar environment near Earth. Yet their presence influences the motion of particles and the behavior of spacecraft traveling beyond the solar system. Early radio observations revealed that interstellar gas emits characteristic signals when its atoms change energy states. Hydrogen, the most abundant element in the universe, produces a specific frequency known as the 21 centimeter line. This signal allowed astronomers to map large regions of interstellar space. The distribution of hydrogen showed that the space between stars contains clouds of varying density rather than a uniform vacuum. Dust grains add another layer to this structure. These grains consist of carbon, silicates, and other solid materials. They are extremely small, often less than a micrometer in size, but they absorb and scatter light. The dimming and reddening of starlight, observed in the early 20th century, provided evidence for this dust. Later, ultraviolet and infrared measurements confirmed that dust plays a significant role in shaping the appearance of the galaxy. Magnetic fields thread through interstellar space as well. Although these fields are weaker than those found near planets or stars, they influence charged particles moving through the region. Measurements from spacecraft, such as Voyager 1 and Voyager 2, showed that the interstellar magnetic field interacts with the solar wind, creating a boundary where the influence of the sun gives way to the environment of the galaxy. Radiation forms another component of this structure. Cosmic rays, high-energy particles accelerated by supernova remnants and other energetic processes, fill interstellar space. These particles move at nearly the speed of light and can penetrate spacecraft materials. Their presence poses challenges for long-duration travel because shielding against them requires substantial math. An everyday comparison helps clarify the idea of structure within low-density regions. Air inside a large warehouse may feel motionless and empty, but it still contains molecules, dust, and temperature gradients that influence sound and airflow. Interstellar space operates on similar principles, but at densities millions of times lower. Even at these levels, small amounts of material and energy accumulate over long distances, creating an environment that must be understood for any attempt at interstellar travel. Interstellar space is therefore not a void. It is a complex medium shaped by atomic interactions, dusty structures, magnetic fields, and radiation. These components form part of the landscape that spacecraft would encounter once they leave the protective environment of the solar system. The speed of light places a structural limit on motion, and this limit shapes every attempt to imagine travel between stars. Light travels at nearly 300 million meters per second, a value established through repeated measurements using planetary reflections, laser ranging, and laboratory experiments. This speed does not depend on the motion of the source or the observer. It is fixed within the framework of special relativity. When an object with mass accelerates, it gains kinetic energy. At familiar speeds, this energy requirement increases in a predictable way, similar to the way a car consumes more fuel as its speed rises. At much higher velocities, the relationship changes. As an object approaches the speed of light, its energy requirement increases sharply. Each small gain in velocity demands a disproportionately large increase in energy. This pattern has been confirmed in particle accelerators for more than a century. Subatomic particles can approach the speed of light, but never reach it. Early theoretical work in the early 20th century predicted this behavior. The equations of special relativity showed that time, distance, and mass interact in ways that prevent material objects from achieving light speed. As velocity increases, time slows for the moving object, and the energy needed for further acceleration grows toward an unbounded value. No known engine or energy source can supply the required increase. A comparison using everyday experience helps illustrate the scale of this limitation. Increasing the speed of a bicycle requires modest effort. Increasing the speed of a car requires considerably more power. Increasing the speed of a spacecraft from 1% of light speed to 2% requires more energy than all chemical propellants used in the history of spaceflight combined. The jump from 90% to 91% of light speed requires more energy than the jump from 1% to 50%. This limit interacts with the structure of interstellar space. Stars are separated by several light years, a scale shaped by gravitational processes over long periods. Even reaching the nearest star demands sustained high velocity. Because the energy requirement grows rapidly as speed increases, no conventional propulsion system can reach or maintain such speeds using known materials. Observational evidence, laboratory measurements, and theoretical predictions all point to the same conclusion. The speed of light defines an upper boundary on motion, and approaching this boundary requires energy inputs beyond any practical capability. This limit remains one of the most fundamental challenges in interstellar travel research. Cosmic radiation forms a persistent background throughout interstellar space. Any spacecraft traveling between stars must move through this environment for long periods of time. The radiation consists of high-energy particles, protons, atomic nuclei, and electrons that originate from powerful cosmic events like exploding stars and active regions of the galaxy. These particles travel at speeds approaching that of light and interact with matter in ways that differ significantly from familiar forms of radiation near Earth. The existence of cosmic radiation was first confirmed in the early 20th century through balloon experiments that measured increasing radiation levels at higher altitudes. Later satellite missions provided direct measurements of particle energies and flux. Instruments aboard probes like Voyager 1 and Voyager 2 recorded the transition from the Sun's protected bubble, the heliosphere, into the broader interstellar radiation field. The data showed that once outside the influence of the Sun, the density of energetic particles rises noticeably. At the scale of everyday life, these particles have no direct parallel. A helpful comparison, however, comes from medical imaging. X-ray machines and radiation therapy devices use photons or particles that deposit energy into tissue. However, cosmic rays often carry energies millions of times greater than those used in medical contexts. When such a particle strikes a spacecraft's material, it can shatter atomic bonds, generate secondary radiation, and pass right through most shielding. The human body responds to this environment in predictable ways. High-energy particles can damage DNA, disrupt cellular processes, and increase long-term risks associated with radiation exposure. Experiments aboard the International Space Station show measurable increases in radiation dose compared with conditions on Earth. Extending these exposures from months to decades introduces challenges that have no established solution using current technology. Spacecraft systems also face risks. Electronic components are sensitive to single-event upsets, moments when a high-energy particle deposits enough energy to alter memory or disrupt the circuits. Engineers mitigate these effects through shielding, redundancy, and error correction. But the effectiveness is limited when the flux of particles remains high for extended periods. The structure of the galaxy ensures that cosmic radiation cannot be avoided during interstellar travel. Exploding stars and other energetic events continually replenish these particles. The result is an environment that remains stable on long timescales. Any spacecraft crossing interstellar space must therefore account for the cumulative effects of radiation on materials, systems, and biological occupants. Cosmic radiation does not form a continuous, solid barrier, but it represents a persistent hazard that accumulates its risk over time. Its presence underscores the difficulty of maintaining human health and spacecraft integrity during multi-decade or multi-century travel between stars. Interstellar dust consists of solid particles that move through space at high relative speeds, and these particles introduce hazards that do not appear in ordinary travel within the solar system. The grains are composed of carbon-rich materials, silicates, and traces of heavier elements formed in the atmospheres of old stars or in the debris of supernova events. Their sizes range from molecules to micrometer-scale fragments, small enough to be invisible to optical instruments, yet capable of damaging a spacecraft traveling at high velocity. The existence of interstellar dust was inferred in the early 20th century, when astronomers noticed that light from distant stars appeared dimmer and redder than expected. This effect, known as interstellar extinction, indicated that dust grains absorbed and scattered specific wavelengths of light. Infrared observations conducted in later decades confirmed the presence of dust clouds spread throughout the galaxy, especially along the plane of the Milky Way. At low velocities, these grains pose little threat. Spacecraft operating near Earth encounter dust regularly, and the impacts rarely exceed the strength of protective surfaces. The situation changes when velocity increases. A particle only a few micrometers across can carry significant kinetic energy when moving at a fraction of light speed. An impact at such speeds can penetrate shielding, generate heat, and create secondary fragments that spread damage across a wider area. An everyday analogy helps illustrate this. Dust carried by wind may leave small marks on a sliding glass door, but a high-speed projectile of similar size can crack or shatter the same surface. The difference arises from kinetic energy, which increases with the square of velocity. In interstellar travel, even slight increases in speed multiply the energy of potential impacts. Measurements collected by spacecraft exiting the solar system show that dust density is low but not negligible. Instruments aboard missions, such as Ulysses and Voyager, detected dust grains moving through interplanetary space that originated outside the solar system. The data indicate that interstellar dust flows through the heliosphere and continues onward into the galaxy, forming streams that reflect the motion of the sun relative to its surroundings. The distribution of dust across the galaxy is shaped by large-scale processes. Stellar winds, supernova shock waves, and magnetic fields transport grains over long distances. Although the densities remain low, the cumulative probability of collision increases during a multi-decade or multi-century journey. This probability becomes a critical factor when designing a craft meant to travel at high velocity. Interstellar dust, therefore, represents a structural hazard for long-distance missions. Its presence requires careful consideration of shielding, materials, and navigation strategies. The hazard does not arise from the amount of dust, but from the combination of particle, energy, and time, both of which amplify the potential for damage during interstellar travel. The energy required for long-distance spaceflight grows rapidly as the desired speed and travel range increase. Within the solar system, chemical rockets provide enough thrust to send probes to nearby planets. These systems combine fuel and oxidizer, releasing energy through combustion. The energy density of chemical propellants, however, is limited by the bonds between atoms in the fuel. This limit becomes apparent when missions are planned beyond planetary orbits. Early rocketry work in the 20th century produced a key result known as the rocket equation. It describes how the change in velocity of a spacecraft depends on the exhaust velocity of its propellant and the ratio between its initial mass and final mass. The equation shows that achieving higher speeds requires either propellants with higher exhaust velocities or a much larger proportion of the spacecraft mass devoted to fuel. In practice, both options encounter strong constraints. In everyday terms, this relationship resembles a vehicle that must carry its own fuel for the entire journey. A car loaded with extra fuel tanks becomes heavier and less efficient. For a rocket, the problem is more extreme because the fuel must also accelerate the fuel that remains on board. As mission designers add more propellant, the usable payload fraction shrinks. The result is a steep rise in mass for each additional gain in speed. Attempts to move beyond chemical propulsion focus on nuclear and electric systems. Nuclear thermal rockets heat propellant using a fusion reactor, achieving higher exhaust velocities than chemical engines. Electric propulsion, such as ion thrusters, expels ions at very high speeds using electromagnetic fields. These methods increase efficiency, but still face limits in total power output and available propellant mass. Interstellar missions highlight these limits. To reach a significant fraction of light speed, a spacecraft must undergo extended periods of acceleration and deceleration. The energy required for these phases scales with the square of the target velocity. If the desired speed doubles, the energy requirement increases by a factor of 4. When this principle is applied to velocities approaching even a small percentage of light speed, the resulting energy demand reaches values comparable to the total yearly energy consumption of industrial civilizations. Historical mission studies have explored theoretical concepts such as fusion-driven propulsion and antimatter engines. These designs rely on reactions with far higher energy densities than chemical combustion. Fusion reactions convert a small fraction of mass into energy, while antimatter annihilation converts all mass into energy. Although these concepts offer large theoretical gains, practical systems capable of storing, controlling, and safely using such reactions have not been realized. The scale of the galaxy magnifies the issue. Travel between stars requires sustained high speed over distances of several light years. Any realistic mission must balance propulsion energy, shielding mass, life support demands, and structural integrity. Energy is not a single component of the design. It interacts with every other parameter, from engine type to ship mass and mission duration. The pattern across chemical, nuclear, and speculative systems remains consistent. The energy payments for long-distance, high-speed spaceflight rise steeply as mission ambitions expand. This rise reflects both physical laws and engineering limits, forming one of the most enduring constraints on practical interstellar travel. Human biology places structural limits on long-duration space travel, especially when the journey extends beyond the solar system. The human body evolved under Earth's gravity, atmosphere, and magnetic protection. When these conditions are removed for extended periods, measurable changes occur in muscles, bones, circulation, and cellular processes. These changes have been documented through decades of research on orbiting stations. Microgravity produces some of the most visible effects. Without the constant pull of gravity, muscles that normally support posture weaken. Bone density decreases because bone-forming cells receive fewer mechanical signals, allowing bone resorption to dominate. These changes occur even during missions lasting only months. Extending exposure to decades, as would be required for interstellar travel, raises concerns about long-term skeletal stability and mobility. Radiation adds another layer of difficulty. Earth's magnetic field shields the surface from most high-energy particles originating from the sun and from distant astrophysical sources. Outside this protective region, astronauts experience increased radiation doses. Measurements aboard the International Space Station show roughly 10 times the annual radiation exposure received on Earth. In interstellar space, where cosmic rays are more intense and persistent, the cumulative dose would increase continuously over the duration of the journey. Circulatory and neurological changes also appear in microgravity. Fluids shift toward the upper body, altering pressure around the eyes and affecting vision in some astronauts. Changes in sleep patterns, circadian rhythm, and mood have been recorded during extended missions. These effects arise from the absence of regular day and night cycles, limited spatial environments, and continuous exposure to artificial lighting. An everyday comparison highlights the scale of adaptation required. A person who remains bedridden for weeks experiences noticeable muscle loss and reduced stamina. Rehabilitation can restore function, but the time needed increases with the duration of inactivity. Spaceflight magnifies this challenge because microgravity removes the need for weight-bearing activity entirely. Even with exercise equipment, the stimulus remains lower than that provided by Earth's gravity. Interstellar travel multiplies all of these concerns. A journey lasting many decades or longer would require systems that allow the body to maintain muscle mass, bone density, and cardiovascular function. Shielding against radiation would need to be far more effective than anything currently used in orbit. Psychological support systems would also be necessary to maintain cognitive health over long periods of isolation. Data from past missions, medical research, and biological models all point toward the same conclusion. Human biology is not optimized for prolonged exposure to microgravity and radiation. These limitations form a fundamental barrier that any interstellar mission carrying human occupants must confront with new technologies or novel solutions. Designing a self-sustaining starship requires a closed system capable of supporting life for periods that exceed the duration of any mission conducted in space to date. Such a system must provide air, water, food, waste processing, and environmental stability without relying on external resupply. The need for long-term reliability shapes every component of the design. The concept of a closed life support system first emerged during mid-20th century research into sealed habitats. Experiments demonstrated that plants could recycle carbon dioxide into oxygen, purify water through transpiration, and provide food in controlled conditions. Later projects, including sealed ecological test beds, confirmed that microorganisms, plants, and humans could form an interconnected cycle of gases and nutrients. However, these systems required careful monitoring because small imbalances grew over time. Water recycling offers a clear example of this principle. Modern spacecraft use systems that recover water from humidity, waste, and other sources. These systems rely on filtration, chemical processing, and distillation. While effective for missions lasting months, extending their performance to multi-decade operations requires higher reliability and redundant pathways. Any failure in the water cycle could compromise the entire environment. Food production introduces additional challenges. Growing crops in a spacecraft demands controlled lighting, temperature regulation, and nutrient delivery. Without gravity, water distributes unevenly through soil, and roots respond differently to their surroundings. Experiments in orbit show that plants can grow in microgravity, but growth rates, structures, and yields vary compared to Earth. A starship would need agricultural modules capable of maintaining stable production across long time spans. Air quality management depends on precise control of carbon dioxide, oxygen, and trace gases. These processes require robust sensors and mechanical systems. On Earth, ecosystems handle these processes through complex interactions among plants, microbes, and soil. Reproducing this complexity inside a spacecraft requires engineered ecosystems that must remain balanced despite fluctuations in crew size, activity, and equipment performance. Waste processing links directly to these cycles. Human and agricultural waste can be broken down by microbial communities into forms that plants can reuse. Achieving this reliably demands stable populations of microorganisms, adequate temperature control, and oxygenation. If any part of the breakdown chain slows or fails, excess waste accumulates and nutrient availability decreases. An everyday comparison illustrates the scale of the challenge. A home aquarium requires constant monitoring to maintain water chemistry and nutrient balance. Minor deviations in pH or temperature can affect the health of its occupants. A closed starship ecosystem scales this complexity by many orders of magnitude. Every parameter, air composition, humidity, lighting, nutrient cycling, microbial activity, must remain within narrow limits for decades. Engineering studies show that such a system is theoretically possible but demanding. The interaction between biological, mechanical, and chemical components introduces many points of potential failure. Developing a starship capable of sustaining itself requires technologies that increase reliability, reduce maintenance, and stabilize ecological dynamics over long intervals. These requirements form a central challenge for interstellar missions that aim to carry human crews rather than automated probes. Generational travel describes missions that extend beyond a single human lifetime, requiring multiple generations to be born, live, and die aboard a spacecraft before it reaches its destination. This concept appears whenever the expected travel time spans many decades or centuries, a duration far longer than any mission in human history. The social, biological, and structural implications of such a journey shape the design and operation of the vessel. Early discussions of generational travel emerged during the mid-20th century, when researchers considered missions to nearby stars using propulsion systems far slower than the speed of light. These studies recognized a basic constraint. If the travel time exceeds the lifespan of the original crew, then their descendants must complete the mission. This transforms the spacecraft from a temporary habitat into a long-term settlement. Population stability becomes a central factor in these scenarios. A viable population must be large enough to maintain genetic diversity across many generations. Studies of closed settlements on Earth, such as remote research stations and isolated island communities, show that small populations face increased risks from limited mate choice, reduced genetic variation, and social pressures. A starship would require careful planning to avoid these conditions. Social structure also plays a significant role. A multi-generational crew would need systems for education, governance, conflict resolution, and resource management. Historical examples from long ocean voyages and isolated communities illustrate that social cohesion depends on shared goals, clear roles, and stable leadership. Without these elements, disputes can escalate and affect mission continuity. Environmental conditions on the spacecraft further influence generational outcomes. Living in a confined space for extended periods can affect psychological health. Limited access to natural landscapes, changing seasons, or fresh stimuli may increase stress and reduce cognitive performance. Long-duration missions conducted in orbit show that even highly trained crews experience pressure from confinement, routine, and environmental monotony. Biological factors amplify these challenges. Growth and development in microgravity or reduced gravity environments may differ from those on Earth. Studies involving animals in orbit show changes in muscle formation, bone development, and sensory responses. Extending these conditions across generations raises questions about long-term adaptation. No experimental data currently describe how multiple human generations would respond to such an environment. An everyday comparison clarifies the scale of responsibility involved. A family maintaining a remote farm must ensure that tools, buildings, and supplies remain functional across years. Small failures accumulate unless repaired promptly. A generational spacecraft multiplies these challenges because every system, from life support to structural components, must remain operational over centuries. Mission design studies indicate that generational travel is theoretically possible, but carries substantial uncertainties. The stability of social systems, the biological adaptation of future generations, and the durability of the spacecraft's infrastructure all require solutions that exceed current experience. These uncertainties form one of the most complex aspects of planning for interstellar travel. Maintaining a functioning civilization aboard a starship requires systems that preserve knowledge, cultural continuity, and social stability across long periods. Interstellar missions, spanning multiple generations, confront challenges that resemble those faced by isolated human communities on Earth, but extend them to a scale lasting decades or centuries without external contact. Historical examples provide useful parallels. Remote island settlements, polar research stations, and early sea voyages operated under conditions of limited resources, constrained environments, and prolonged isolation. In each case, long-term stability depended on education, shared norms, and reliable communication within the community. Breakdowns in these systems often produced social fragmentation or operational failures. A starship magnifies these pressures because the environment is fully enclosed. The crew must rely on technology to regulate air, water, temperature, and waste. Any disruption in these systems affects the entire population. Social structures must therefore include trained personnel who understand engineering, biology, medicine, and governance. Knowledge cannot be lost across generations, and education systems must function continuously. Cultural continuity plays a central role in stability. A crew that views itself as part of a mission with a clear purpose is more likely to maintain cohesion. If later generations lose connection to the original goal, the mission could drift toward competing interpretations or conflict. Anthropological studies show that communities preserve stability when social rules, rituals, and shared narratives reinforce collective identity. Population dynamics introduce additional complexity. The number of individuals cannot grow indefinitely because the ship has fixed resources and space. Systems that guide reproduction, family structure, and resource distribution must remain predictable and fair to avoid destabilizing pressures. Earth-based examples, such as communal settlements or closed ecological habitats, illustrate how imbalances in resource allocation can lead to disputes. Psychological health is another essential factor. Extended confinement can produce stress, reduced motivation, and tension within groups. Observations from space missions, submarines, and remote stations show that rotation of tasks, access to varied environments, and regular communication reduce psychological strain. A starship would require artificial day and night cycles, recreational activities, and spaces designed to minimize monotony. Technological maintenance intersects with social stability. Critical systems must be repaired and updated across generations. Skills can degrade if training becomes inconsistent or if knowledge is transmitted inaccurately. Earth-based industries demonstrate that long-term reliability depends on documentation, apprenticeships, and redundancy in expertise. Taken together, these factors show that maintaining a civilization between stars depends not only on engineering, but also on sociology, psychology, and cultural design. A starship becomes an isolated society whose success relies on stable institutions, durable knowledge, and a shared understanding of the mission over long spans of time. Earth remains the most stable environment known for sustaining human life, and this stability highlights the contrast between planetary habitats and the conditions expected during interstellar travel. The planet provides gravity, atmospheric pressure, a magnetic shield, and a continuous supply of natural resources. These features reduce the need for artificial systems and allow biological processes to proceed within familiar ranges. Gravity plays a central role in maintaining long-term health. Bone density, muscle strength, and circulatory patterns all depend on the constant pull of Earth's surface. Microgravity environments, such as those found in orbit, produce noticeable changes within months. These changes can be managed for short missions, but become increasingly difficult to counter during multi-decade periods. Earth's magnetic field and atmosphere form a protective barrier against high-energy particles. The magnetosphere deflects charged particles, while the atmosphere absorbs and scatters cosmic radiation. Together, these layers reduce the radiation dose received by organisms on the surface. In interstellar space, this protection disappears. Shielding must be entirely artificial, adding mass and complexity to spacecraft design. Resource availability represents another difference. On Earth, water cycles through evaporation, condensation, and precipitation. Plants grow in soil that receives nutrients through geological and biological processes. Waste breaks down through microbial action and reintegrates into the environment. These cycles proceed without mechanical intervention. A starship must replicate these cycles through engineered systems that require constant monitoring. Psychological factors also contribute to Earth's relative safety. The planet provides varied landscapes, changing weather, natural sounds, and the daily cycle of sunlight and darkness. These stimuli support cognitive health and emotional stability. Enclosed environments, such as those found on ships or stations, can produce monotony and stress when extended for long periods. Interstellar missions would magnify these effects by removing opportunities for escape or resupply. Historical analogs show similar patterns on smaller scales. Polar stations, submarines, and long-duration space missions operate in isolated conditions that restrict external interaction. Crews in these environments manage stress through structure, routine, and communication with support teams. Even with these measures, psychological strain increases over time. Earth's stability derives from the interplay of geological, atmospheric, and biological systems that developed over billions of years. These systems create a balanced environment that supports life with minimal intervention. In contrast, a starship must recreate each component of this balance artificially. Any failure, even minor, carries consequences that accumulate over time. For these reasons, Earth remains a uniquely safe harbor. The contrast between planetary stability and the challenges of interstellar space underscores why long-distance missions require technologies and systems far more robust than those used for travel within the solar system. Fusion-powered starships represent one of the most extensively studied concepts for achieving higher velocities in interstellar travel. Fusion reactions release large amounts of energy by combining light atomic nuclei, typically isotopes of hydrogen. This process occurs naturally in the cores of stars and has been reproduced in controlled conditions on Earth for brief periods. The energy density of fusion exceeds that of chemical propulsion by several orders of magnitude. Early theoretical studies, including mid-20th century proposals, examined how fusion could be used to propel spacecraft. The most well-known among these is Project Daedalus, a study conducted in the 1970s by the British Interplanetary Society. Daedalus proposed a two-stage fusion engine using pellets of deuterium and helium-3 ignited by electron beams. The concept projected a cruise velocity approaching 10% of the speed of light, allowing a journey to a nearby star within several decades. The design relied on inertial confinement fusion, a technique in which small fuel pellets are rapidly compressed and heated to trigger fusion. Laboratory experiments have demonstrated fusion using similar methods, but sustaining the process at the scale required for propulsion remains beyond current technology. Fusion reactors on Earth require large facilities, precise control systems, and significant energy input relative to output. Magnetic confinement fusion provides another potential approach. Instead of compressing fuel pellets, this method traps plasma-ionized gas composed of hydrogen isotopes within magnetic fields. Devices such as tokamaks and stellarators attempt to maintain plasma stability long enough for fusion reactions to occur. While progress has been made, no magnetic confinement system has yet produced more energy than it consumes. Scaling such systems for spaceflight introduces additional challenges, including mass reduction, reliability, and long-duration operation. A comparison to familiar technologies highlights the gap between concept and implementation. Commercial jet engines operate continuously for thousands of hours with predictable performance. Fusion systems, by contrast, have only achieved reaction times measured in seconds. Extending these reactions to uninterrupted operation over years or decades requires advances in materials, control algorithms, and energy management. Fuel availability also shapes the feasibility of fusion propulsion. Helium-3, a key ingredient in many proposed designs, is rare on Earth. Theoretical sources include the lunar surface and the atmospheres of gas giants, but extracting meaningful quantities would require large-scale industrial operations. Deuterium is more abundant, yet pure deuterium fusion produces high-energy neutrons that complicate shielding and structural design. Despite these challenges, fusion-powered starships continue to receive attention because they offer a pathway to velocities significantly higher than those achievable with chemical or nuclear thermal systems. The combination of high energy density and relatively low mass consumption makes fusion an appealing long-term goal. Current research indicates that fusion propulsion is theoretically sound, but technologically distant. Achieving the necessary performance requires breakthroughs in reactor stability, energy efficiency, fuel processing, and long-duration system reliability. These requirements define the frontier for future interstellar propulsion research. Light sail propulsion relies on the momentum carried by photons to accelerate a spacecraft. Photons have no mass, but they possess momentum that can be transferred to a reflective surface. When large, lightweight sails intercept streams of light, the cumulative push produces continuous acceleration. Over long durations, this push allows a craft to reach high velocities without carrying onboard propellant. The basic principle was recognized in the early 20th century, when physicists studying electromagnetic radiation noted that light exerts pressure. Early experiments used delicate instruments to measure this force in laboratory settings. Although extremely small in everyday contexts, the pressure becomes significant when applied over large areas under sustained illumination. Two primary sources of photon pressure are available: sunlight and directed laser beams. Solar sails use the natural output of the sunday. Several missions, including Japan's Icarus and the Planetary Society's Light Sail projects, demonstrated controlled flight using sunlight alone. These missions confirmed that photon pressure can change trajectory, adjust orientation, and produce measurable acceleration. Laser-driven sails represent a more ambitious approach. Instead of relying on sunlight, ground-based or orbital lasers concentrate energy onto the sail. The breakthrough Starshot initiative, proposed in the early 21st century, outlined a system in which powerful lasers would accelerate a gram-scale probe to a significant fraction of light speed. The concept called for a reflective sail only a few meters across and built from extremely lightweight materials. An everyday comparison clarifies the difference between solar and laser sails. A traditional sailboat moves when wind transfers momentum to its sails. The effect is limited by wind speed. A boat pushed by a directed jet of air from a turbine could, in theory, accelerate more rapidly. Laser sails operate on a similar principle, replacing air with concentrated streams of photons. The momentum transfer remains small per photon, but the combined effect of trillions of photons per second produces a sustained force. Material science shapes the feasibility of photon-propelled travel. Sails must be lightweight, reflective, and capable of withstanding intense illumination. Heat management becomes critical because absorbed energy can damage the sail. Engineers also must address issues of stability. Photon pressure can cause the sail to deform or rotate unless its shape and mass distribution remain carefully tuned. Navigational challenges also arise at high velocities. A laser-driven probe must maintain alignment with the beam during acceleration. Small deviations can reduce efficiency or cause the craft to drift away from the intended path. Maintaining communication over interstellar distances adds another layer of complexity. Despite these challenges, photon sail propulsion offers one of the most realistic paths toward interstellar travel using near-term technology. Unlike fusion or antimatter engines, photon sails do not require storing large quantities of fuel. They rely on externally supplied energy and lightweight structures. Research continues on materials, beam focusing, and guidance techniques. Light sail systems remain in the conceptual stage for interstellar missions, but the principles have been validated at smaller scales. Achieving interstellar velocities requires major advances in power generation, laser infrastructure, and sail durability. Even so, photon propulsion is currently one of the few methods theoretically capable of reaching nearby star systems within timescales shorter than centuries. Wormholes appear in theoretical physics as possible shortcuts through space-time, but their use for travel remains speculative. The concept arises from solutions to the equations of general relativity. These solutions suggest that space-time can curve not only around massive objects, but also in configurations that create tunnels linking distant regions. Such structures, if they exist, would allow a traveler to cross large distances without moving through the space between. The idea entered scientific discussion in the early 20th century when researchers studying Einstein's field equations identified geometries that resembled bridges between separate points. Later work showed that these structures could exist only under very specific conditions. They would require forms of matter with unusual properties, including negative energy density. No known material exhibits these characteristics in stable quantities. Efforts to explore the physics of wormholes rely on mathematical analysis rather than direct observation. Astronomical surveys have not identified any phenomena that can be conclusively interpreted as wormholes. Signals from distant stars and galaxies follow predictable patterns based on gravitational effects, radiation processes, and cosmic expansion. None display the abrupt distortions that would suggest the presence of a traversable tunnel. An everyday analogy helps illustrate the difference between theoretical possibility and practical application. A folded map can place two distant cities next to each other when the paper bends, even though the actual distance on the ground remains unchanged. Wormholes represent a similar geometric transformation. The equations allow the folding, but creating or stabilizing the fold requires conditions that are not accessible with current technology. Quantum field theory introduces additional complications. The energies and pressures required to maintain a wormhole throat, the region that connects one opening to another, tend to produce instabilities. Small fluctuations can cause the structure to collapse before anything can pass through. Attempts to counteract these instabilities with exotic matter remain theoretical because no experiment has produced the required material in macroscopic amounts. Even if a stable wormhole could be created, navigation would pose challenges. A craft entering one opening would need precise control to avoid tidal forces at the throat. The exit point might lie in a region of space with different radiation levels, gravitational conditions, or relative velocities. Communication through the structure would also require systems capable of handling rapid changes in space-time geometry. Historical studies of speculative propulsion concepts often include wormholes because they bypass the speed limitations imposed by relativity. However, these studies consistently conclude that the theoretical requirements exceed practical capabilities. No mechanism currently exists to create, locate, or stabilize such a structure. Wormholes remain an intriguing feature of theoretical physics. They demonstrate how the equations governing space-time emit a wide range of geometries. For interstellar travel, they highlight a boundary between mathematical possibility and technological reality. Their study continues to inform research into gravity and quantum fields, but their use as transportation pathways remains beyond foreseeable engineering. Time dilation becomes significant when an object approaches a substantial fraction of the speed of light. According to special relativity, the passage of time depends on the relative motion between observers. A moving clock runs more slowly than a stationary one when measured from the stationary frame. This effect remains extremely small at everyday speeds, but becomes measurable as velocity increases. Early experimental evidence for time dilation came from observations of muon subatomic particles created in Earth's upper atmosphere by cosmic rays. Muons have short lifespans, but detectors at the surface record more muons than expected if their decay times remained unchanged. Their high velocities allow them to survive longer because time passes more slowly in their frame of reference. Particle accelerators later confirmed this behavior under controlled conditions. For spacecraft attempting interstellar travel, time dilation introduces both challenges and opportunities. If a craft reaches 10% of light speed, the difference in time between the ship and Earth remains modest. As velocity rises further, the effect grows. At velocities near light speed, a journey lasting decades on the ship might correspond to centuries passing on Earth. This separation influences communication, mission planning, and the relationship between crew and home planet. An everyday comparison helps clarify the idea. Two clocks placed in different environments can drift slightly due to variations in temperature or mechanical wear. In relativity, the drift arises not from imperfections, but from the structure of space-time. The faster an object moves, the more its timescale deviates from that of a stationary observer. The effect interacts with the structure of the galaxy. Stars orbit the galactic center at various speeds, and their relative motions influence travel paths. A high-speed craft moving through this environment experiences a different timeline than the regions it passes. When it eventually slows down or arrives at a destination, the local time may differ significantly from the time experienced on board. Engineering considerations arise as well. Maintaining structural integrity, communication systems, and navigation accuracy requires accounting for relativistic shifts. Signals sent to and from the craft experience Doppler effects that modify frequency. Navigation based on external references must adjust for the fact that clocks inside the craft run at different rates than those used for timing measurements. Biological processes follow these relativistic shifts as well. From the perspective of the crew, aging proceeds normally. From the perspective of observers remaining on Earth, The crew ages more slowly. This difference does not reduce the physical strain of long-duration spaceflight, but it alters the relationship between crew and their place of origin. Time dilation does not provide a method for exceeding the speed of light, but it reveals how near light speed travel changes the experience of time. For interstellar missions, the effect becomes a fundamental part of planning. Understanding it ensures that navigation, communication, and mission timelines remain consistent across the differing frames of reference involved. Attempting to cross the distances between stars forces a reassessment of how humans understand scale, technology, and long-term planning. Interstellar space extends far beyond the limits encountered in planetary exploration. The challenges identified in propulsion, biology, energy, and social structure reveal that such a mission is not only a technical undertaking, but also an examination of how civilizations approach goals that span generations. Early astronomical observations showed that stars form, age, and move through the galaxy on timescales far longer than human history. Their arrangement reflects gravitational processes operating over millions of years. When mission planners consider travel across these distances, they must align human activity with structures shaped by cosmic evolution. This mismatch between human time and cosmic time defines much of the difficulty. Technological ambition plays a central role. Every major concept for interstellar travel, fusion engines, photon sails, nuclear systems, or speculative shortcuts, represents an attempt to match the scale of the environment. Each solution pushes the boundaries of engineering. The effort reflects a pattern seen throughout history. Tools are developed to meet challenges that exceed existing capabilities. Interstellar travel magnifies this pattern by requiring sustained innovation across many fields. The decision to pursue such a mission raises broader questions about purpose. Explorers throughout history crossed oceans and continents to understand their surroundings or procure resources. Interstellar travel offers no immediate practical reward. Instead, it connects to deeper motivations: curiosity, long-term survival, and the desire to expand knowledge beyond current limits. These motivations align with scientific inquiry, which often proceeds without immediate application. An everyday analogy helps clarify this perspective. Planting trees that take decades to mature requires accepting that the benefit will be realized by future generations. Interstellar missions follow a similar pattern. The work done by one generation may serve a distant outcome that only later generations will witness. This shift in perspective influences how societies evaluate investment, commitment, and responsibility. The structure of the galaxy also suggests that interstellar travel is part of a larger narrative. Stars move through spiral arms, encounter regions of higher density, and undergo changes influenced by gravitational interactions. Planets form, evolve, and sometimes support life. Within this cosmic setting, the act of attempting a journey between stars becomes one more expression of how living systems adapt to their environment. Interstellar travel remains beyond current capability, yet the study of its challenges provides insight into engineering, biology, sociology, and physics. Each barrier highlights the extent to which human knowledge must expand before such missions become viable. Considering these challenges clarifies the scale of the universe and the position of human civilization within it. The effort to understand and plan for these journeys demonstrates how the search for knowledge extends across time. It shows that the attempt to cross the stars, even if unrealized, shapes scientific progress and deepens the understanding of how life interacts with the broader structure of the cosmos.